Swayam Prabha. Digital India. Educated India.
So, we have been discussing about features which are exclusive to Fourier transform NMR. We talked about various important parts in that one. So, we will continue with that discussion with regard to the special features which are exclusive for FT-NMR. In that one we now come to the 10th point, which is phase correction. Typically we know that NMR signals are of two types. One, we have a signal which is like this, and this we call as absorptive signal, or you may call this also as a spectrum with a 0 phase, or the other is the dispersive signal which goes like this, and this is a dispersive signal, and this we may call it as 90-degree phase. In FT-NMR we collect the data as, let us say we collect the data is cosine omega I t and e to the minus lambda t, lambda I t. Suppose we have the signal which is like this. When you Fourier transform this, it generates two components, one is the real component and then you also have the imaginary component. Time domain function, this is my FID. If FID is like this, the real part will have a pure phase absorptive signal, this is absorptive, and the imaginary part will have the dispersive component. Okay. Now similarly, if my FID is of the type sine omega I t e to the minus lambda I t, if I have this sort of a function FID, this is my FID, then after Fourier transformation I will get again a real part and an imaginary part. The real part will have the dispersive signal and the imaginary part will have the absorptive signal. Okay. So therefore we have to see what is it that we are going to get in a FT-NMR spectrum. Okay. Now often we find that your signal is not exactly dispersive or absorptive, sometimes we get signals which are like this. Okay. Okay, so this is a mixture of absorptive and dispersive signals. Okay, so therefore this is known as phase error. So this is called as phase error and this has to be corrected. Okay. So now what is the source of the phase error? What causes the phase error? This we have to understand. Okay. Now as I explained to you, suppose I have the experiment done like this. I have the initial magnetization here, this is the m naught, initial magnetization which is here. If I apply a 90-degree pulse along the x axis which is exactly correct 90x, then my magnetization will come along the, let us say, the y axis. whether it is 90x or minus x, if it comes exactly along the y axis, then my signal will be cosine omega I t e to the minus lambda I t. Okay. This will be my signal if I collect the signal starting from the exactly magnetization aligned along the y axis. Okay. But often it so happens that this is not achieved. This is not achieved, and what happens is you get the magnetization which was initially rotating to somewhere like this, to some other position. So, then it will be oriented here in the transverse plane. If this is the case, then you have the x, y and z. So, the signal which you are going to collect will have the contributions coming from this as well as from this, right. So, if it is not 0 phase, this is let us say this angle is theta, then theta is the phase at time t is equal to 0. Okay. So, in the such a situation, your signal will have real component which is the cosine component, cosine omega I t, and also sine omega I t. Okay. So, signal will have both the components. So, if I Fourier transform this, what I should get? Of course, this will have a certain amplitude here, there is a coefficient, let us call this as A1 and call this as A2. There are 2 coefficients depending upon what is the error here, theta error, depending upon that the components along the y and the x axis will be different. Whatever is along the y axis will have a cosine omega I t, whatever is along the x axis will be the sine omega I t. Now, if I do a Fourier transformation of this sum together which is collected here, I will have a mixture of in the real part, okay, it is also true in the imaginary part also. This is the absorptive component, and then I will also have a component which is coming from the x part which is the dispersive component. This plus this will give me a signal which is like this. So, this is because of the error in the initial pulse application. The pulse is not applied exactly along the x axis, but slightly deviated from the x axis. So, RF phase is not exactly 0, but slightly away, and that is the theta. Therefore, when the 90-degree rotation happens, it does not come exactly along the y axis, but it comes somewhere in the xy plane, and that if the angle is theta, there is a certain mixture of these 2 things will happen. So, this has to be corrected, okay, and this is called as a 0 order phase. 0 order phase error, because this is not dependent on any frequency, entire magnetization is rotated. So, at time t is equal to 0, all the magnetization components have the same angle. At t is equal to 0, all the components have the same phase error. And in the this is in the real part. The imaginary part similarly will have this portion will have pure dispersive component and also a small absorptive component. Okay. So, the trick in correcting the phase will be to mix these 2 appropriately, so that the dispersive component from the absorptive signal will vanish, and likewise the absorptive component from the imaginary part will vanish. Okay. So, that is the idea. Okay. Now, there is another source of phase error, and that is the following. Suppose my FID is supposed to be like this, right, and my data points are should be like this, here, here, here here should be like this. Okay. So therefore at time t is equal to 0, the magnetization is entirely along the y axis or whatever that is. Okay. See, in this case the magnetization is entirely along the y axis if I am collecting the y components. But suppose I cause a small delay in the acquisition of the time. So in this situation, where will the magnetization be? All the components of magnetization will be along here, all the components. So this will be, all the components will be here in this case, the normal case this is. But instead suppose I do not start collecting the data from time t is equal to 0, this is at t is equal to 0. Now if I collect the data, this is my FID, but I do not start collecting the data from the first point, but I start collecting from here. Okay, I give some delay for various practical reasons, I do not collect this. So this can be a small time also, it can be a few hundred nanoseconds, that is, it has nothing to do with the dwell time, it has some hardware limitations. So you may want to give a small delay here, this is a small delay, we may call it as T naught. So your actually data collection starts from T naught. So therefore your signal here will be cosine omega I t plus T naught. Okay. So what does that mean? If I were to represent this in the transverse plane like this, the magnetization, where it will be to start with? To start with, we are because the T naught is the delay, during this period time the different components will have precessed to different extents, right. So during the time T naught the various components would have precessed, although I applied a 90-degree pulse correctly, that it came to the y axis, the magnetization came to the y axis, but I did not start collecting the magnetization from that point. I started collecting when the different components have moved to different extents, that is T naught. So let us say one component has moved here and another component has moved here, okay, and the third component would have moved here, okay. These are different spins, different lines in your spectrum, they are corresponding to different spins. So they all have moved to different extents, let us call this as 1, 2, 3, and all of these now have different thetas, right. They all have different thetas. Compared to the previous one, it was a 0 order phase. Now in this case, because of the delay in the data acquisition, the different frequency components in your magnetization have moved to different extents. Therefore the first line would have a mixture something like this, okay, let me call this as 1, and the second one may have had some more here, and the third one would have even more, third, and so on. So different ones will have different mixtures. Therefore this is what we call it as frequency dependent phase shift, and this is what we are talking about, these are all in the real part of the spectrum. Similar thing will happen in the imaginary part of the spectrum. So in order to correct for this here as well as in the previous case, the strategy is to mix the real and the imaginary components, okay. So therefore phase correction would imply mix the real and imaginary parts appropriately to eliminate the admixture. The computer does this, there are various kinds of knobs over there, so you just keep moving the knobs, and in real time actually you can monitor on the screen how the phases are changing. So these algorithms are there, this is the mathematics behind this, all that is all programmed into the computer, it is all programmed how to mix the real and the imaginary parts and what should be the coefficients for the mixing, all that is done, you can manually adjust it. So this can be manually adjusted. Okay, to obtain the phase correction. Then we will have, after you have done that, you get pure absorptive line for the real part and pure dispersive part for the imaginary part. You generally do not use the imaginary part for other purposes. When you want to represent your spectrum, you only plot the real part, you only plot the absorptive spectrum, right. Imaginary part stays there in the computer, but you do not really look at that. However, it is used for phase correction. So that is the important part of the Fourier transform NMR, and this does not exist in case of conventional spectroscopy. Okay. So now moving on to the next important concept, and that is dynamic range. So what is dynamic range? Let us say we have a small signal and a huge signal like this. This may be a solvent, this may be from your sample. And you notice in Fourier transform NMR we excite all of them together. Okay. In FT-NMR all these are excited together and signal is digitized. So when I collect the data in the digitized form, it will be superposition of the contributions from all of those. Okay. Suppose this signal has intensity of 1, this signal has intensity of 100, then what I will be collecting will be 101. If this is 5 and this is 200, what I will be collecting will be 205. Okay. So that is what I will be representing in my FID. So this is what happens in the FID. The FID which you have this, you have the various points at various places, and in every point we will have this summation represented. Okay. Therefore, in every point the data has to be represented correctly, this sum has to be represented correctly. How it is stored? How it is stored in the data? The data is digitized, right, as I told you, data is digitized, and there is this device which is called as analog to digital converter. Analog to digital converter, also called as ADC. Okay. This collects data in the binary form. Okay. So it does collect data in the binary form, because that is what the computer understands, right. And let us say we have an analog to digital converter which has a resolution of about, let us say 4. So there are 4 bits. There are 4 bits in the analog to digital converter. What is this? This will be 2 to the power 0, 2 to the power 1, 2 to the power 2 and 2 to the power 3. So what is the largest number that can be stored here? 2 to the power 0 is 1, this is 2, this is 4 and this is 8. This is equal to 15. This is a 4 bit digitizer. Each one of them is called as a bit. The 4 bit digitizer, the largest number is 15, that is 2 to the power 4 minus 1. This of course is a very small number. Typically our intensity ranges will not be so small, they will be much larger than this. We would like to have as a large a range as possible. Okay. So therefore typically one uses what are called as 12 bit digitizer, 12 bit or 16 bit. 16-bit digitizer. So out of these they also have to account for the sign. One bit is kept for the sign, plus or minus, one bit is kept for the sign. So therefore what will be the number in this a 12-bit digitizer? Okay. In a 12-bit digitizer 1 plus 11, this is for the sign, and 11 bits, what it will give you? 2 to the power 11 minus 1. 2 to the power 11 is 2048 minus 1, that is equal to 2047. Okay. So this is the largest number that you can store. Therefore in your FID, the digital point should, when you add up the intensities of the small signal and the large signal, it should be below 2047. Or let us say if you scale it, for some reason you have a possibility of scaling it down, I multiply everything by scaling factor like 1 by 5 or 1 by 10 or something, that is a scaling factor. Even so, that scaled number should be less than this. In other words, the ratio of large signal to small signal should be less than 2047. Then the whole thing will be represented, and this is where the problem comes. Let us consider that you are collecting a signal in water. Consider a sample in water, and we are recording the proton spectrum. Proton spectrum, what is the concentration of proton here in water? So this is approximately 110 molar. Water proton is 110 molar, and if we have a sample which is 1 millimolar, what is this concentration? This is 10 to the minus 3 molar. Okay. And therefore what is the ratio? The ratio is equal to 110 divided by 10 to the minus 3, this is approximately 1.1 into 10 to the power 5. Okay. So therefore it is impossible to represent this number in this 12-bit digitizer, and this is called as the dynamic range. In such a situation, the small signal gets lost. Only the big signal is represented and the small signal is not represented. Okay. This is called as dynamic range problem. Okay. This is the problem. So what should we do to avoid this? We have to devise techniques to suppress the strong signal. Most often the strong signal is from your solvent. Okay. It is not of much use for you to collect a water signals, solvent signal. Therefore you can suppress that strong signal, and so that you can observe your actual signals. And there are various strategies to do this. So therefore we will come to the next topic, which is called as the solvent suppression. Okay. There are various strategies to do this. Okay. I will take you some of the very simple ones there, and of course there are very elegant procedures which are there, we will see how to use them. Okay. The simplest thing is first the pre-saturation. So what is the strategy here? Let me represent my FT-NMR experiment in this manner. This is my 90-degree pulse, and I am actually collecting the signal here as a FID. This is my FID. Okay. So, what I will do is, before I apply the 90-degree pulse, I apply a soft RF, another RF. I do not use the same RF which is here. I will use the soft RF here on water. That is the solvent signal. That means it will excite only the water, it will not excite anything else. So, this will saturate the water signal, this will saturate the water. And it will not affect anything else because it is soft. So, it is applied exclusively to the water signal, therefore, it will only saturate the water. Now, before that saturated water returns back to equilibrium, before it comes back, you apply 90-degree pulse here or whatever the flip angle you want to use, and then you detect the signal. You finish your experiment before the water comes back. Okay. So, therefore, in this area the solvent contribution will be reduced. Okay. So, this is the simplest of the experiments, and there are other methods. We will see what is called as the inversion recovery. We will see the next experiment which is called as the inversion recovery. Let me call this as A. Okay. Then I will say B. B is inversion recovery. Inversion recovery technique. So, what we do here is it actually uses more than one pulse here. So, the strategy will be like this: you apply a 180-degree pulse, a hard pulse, give a time tau, wait for a time tau, and then you apply a 90-degree pulse or flip angle, whatever flip angle you want to give, and you collect the FID here. How does this work? Let us try to understand this in a vectorial manner, vectorial picture. Inversion recovery means 180-degree x plus, meaning what? The magnetization is rotated from here to here, right. Initially magnetization was here and that gets rotated to this point when you have a 180-degree pulse. So, let me draw that as here. Now, this magnetization contains contributions from not only from the water, but also from your other signals, from your other samples as well. Let me represent them with a different color. So, let us say I have another one here, for 2 is enough for purposes of understanding. Now, both these will try to recover back to equilibrium. Okay. Now, what you do is, suppose my red is water and the green one is my sample. Okay. So, in that situation what I will do is, I will adjust tau such that water has come here because it is recovering. As it is recovering, water has come here at 0 point, and but the green one has come here. Okay. So, which means they have different relaxation times. The red water and the sample, water and the sample have different T1 values, because this is T1 relaxation, right. This is the longitudinal magnetization. Longitudinal magnetization is what is happening here. This is here, what is happening here is T1 recovery. During the time tau there is a T1 based recovery. So, if the two have different T1 values, I adjust the time tau in such a way that the red signal which has come down to 0, but the green one has gone up or either down, either way it is possible. It may not have reached there or it has crossed that. Okay. Now, after this, if I apply a 90x pulse, I will not get any signal from the water. Ideally I will get only signal from the sample. However, in practice this does not happen. Some signal will always come because the recovery is not all that very precise, adjustment is not so precise. So, this is a strategy. This of course requires that have distinctly different values, things which are very distinctly different values, only then you can suppress the water. If they have similar relaxation times, then this will not work, okay, because if the water has relaxed to 0, your sample also would have relaxed to 0, okay. So, then you may lose that, and then of course if the difference is not very large, in T1 is not very large, then your sample also will get attenuated. Sample signal will also be attenuated. Okay. So, this is an important technique. Okay. Now then we will stop here, and in the next one we will continue with this and take more.